Good evening, everybody. Again, hi, my name is Ian Latimer. I'm a project manager on NYSERDA's Clean Energy Siting team, and it is my distinct pleasure to welcome you all to the first event in NYSERDA's forthcoming webinar series entitled Battery Energy Storage Systems, Key Considerations for Local Governments. As you all know, or are soon to know, energy storage plays an exciting and growing role in New York's clean energy landscape, so it's great to have you all with us tonight to learn more about this important technology. Next slide, please. Just real quick, we're going to go ahead and go over some housekeeping considerations before we kick off this evening's webinar. Attendees are muted upon entry, and so you'll see that little icon when your microphone is muted. That said, questions and comments may be submitted in writing during the Q&A, or during the event rather, at any time using the Q&A feature. If you want to take a brief moment to identify that so that you know where to go when you have a question, please do. Additionally, if you have a question about information contained on a specific slide, please note the slide number in your question, which can be found in the lower right-hand corner of the slide. Today's webinar, a recording of today's webinar, along with the slides, will be posted on NYSERDA's website following the event at www.nyserda.ny.gov/storage guidebook, where you can also find our resources for local governments. And additionally, if any technical issues arise during the webinar, please contact my colleague Sal Graven. You can reach him at sal.graven@nyserda.ny.gov. Next slide, please. And one final item before we get into tonight's presentation. As a reminder, tonight is the first part in a 5-part series of bi-weekly webinars on energy storage for local governments. Throughout this series, we will be hearing from a variety of subject matter experts, with each session focused on a different consideration related to energy storage, which is of particular import to local government officials. You can see the list of those sessions here. The second webinar will focus on fire safety, the third webinar on zoning and permitting for energy storage, the third webinar, or the fourth webinar rather, on decommissioning and end-of-life considerations for energy storage systems. And finally, we'll round out the series with a session on taxation and assessments. Now, we welcome all attendees to register and attend each of these sessions, which may be of interest to you. You should be able to access registration links for each individual session in the same place that you found the registration link for tonight's webinar. Next slide, please. And with all of those introductions, we'll now go ahead and go over the agenda for tonight's session. We will begin by going over an introduction to New York State's goals, programs, and resources regarding clean energy and energy storage systems specifically. From there, we will go ahead and address Battery Energy Storage Systems 101, the main event of tonight's webinar. From there, we'll spend a few minutes covering some battery energy storage system fact versus fiction in a few different categories. And finally, we'll round out this evening's presentation with a Q&A featuring our presenters. And speaking of our presenters, next slide, please. It's my sincere pleasure to introduce our 2 speakers for this evening's webinar. Up first, you'll be hearing from my colleague Jason Doling, who's held a number of noteworthy hats throughout his time at NYSERDA. Prior to his recent tenure as NYSERDA's acting chief of staff, and perhaps most relevant to tonight's webinar, Jason served as the program manager for NYSERDA's energy storage program. And in that role, Jason was a co-lead in creating New York's energy storage roadmap and assisted with the creation of the New York Battery Energy Storage Technology Consortium, which is known by many as New York BEST. It is also my sincere pleasure to introduce Dr. Stanley Whittingham, the Distinguished Professor of Chemistry at Binghamton University and Director of the Northeast Center for Chemical Energy Storage. Dr. Whittingham's remarkable career has centered on the research and development of lithium-ion batteries, beginning with his discovery of the role of intercalation in batteries in the early 1970s, leading to his invention of the first rechargeable lithium-ion battery in the late 1970s, and notably culminating in his recognition as a 2019 Nobel laureate for chemistry. Dr. Whittingham received his bachelor's, master's, and doctorate of philosophy, each in chemistry, from Oxford University, and we've been pleased to count him as a New Yorker since he joined the faculty at Binghamton University in 1988. Now, we'll be hearing from Dr. Whittingham a bit later in tonight's program, but in the meantime, I'm going to pass over the microphone to my colleague Jason Doling, who will get us kicked off this evening. So next slide, please, and Jason, the floor is yours.
Thanks, Ian, and welcome everyone. And I do want to take a moment just to thank Ian for all of his hard work in putting this together. He really is the brainchild behind this series and had been identifying topics that were frequently asked questions whenever he and his colleagues would travel the state up until about just over a year ago. So what I would like to do, and I'm only going to take about maybe 5 minutes, I just want to set the stage to explain why some of the driving forces are bringing energy storage onto the grid, what it is going to do on the grid, and really just help put a little bit of perspective for everyone on the call in terms of you may not have heard a whole lot about energy storage, and now all of a sudden you're seeing developers come in and talk to you, and you're seeing applications come in. So really underpinning quite a bit of this is the Climate Leadership and Community Protection Act that was signed into law in 2019. And most important on here is that it really sets New York on a path for a zero-emission electric sector and for decarbonizing the broader economy. And that is going to be pretty meaningful as we advance to the next slide, which is taking a historical look. Go one more if you could. If you think about the way the grid has historically worked, it really is the world's best just-in-time machine. Electricity is literally produced in almost the moment that it's consumed, and it can travel the span of Buffalo down to New York City within less than a second. And the only way historically that we have been able to store energy has traditionally been pumped hydro. There's 2 large facilities comprising just about 1,400 megawatts, one just south of Albany, one out near Buffalo. And if you think about when pumped hydro started to come in place, it was largely during the proliferation of nuclear energy, when nuclear plants really like to run to constant baseline power, and nighttime would hit, and you would have an excess, and you would have to store it. That's actually a pretty good parallel for why we're seeing storage today. As we look to decarbonize the electric sector, what we really need is a way to actually time shift clean generation to when we need it. So obviously when the wind's blowing at night, a lot of people are not using a ton of electricity, and we want to be able to store that and use it when it's needed, but then also where it's needed. So when you look at the very bottom of this, it's a couple of years dated, but it's actually still pretty illustrative. The darker orange is actually the nuclear fleet in New York State, and that shows the percentage of total generation that was coming from that fleet. That's actually going to start decreasing in the coming years as Indian Point, just north of New York City, has now fully shut down. The other part that I'll call your attention to is the purple. So that's natural gas, which is one of the largest sources of electric power generation in the state. However, as the requirements of CLCPA, the climate law, take effect, it's not possible to simultaneously meet the emissions reduction goals and remove that carbon and the pollution while also bringing renewables online without having the ability to store them. I'll finally point out that within the law, the storage target was actually codified. You see that on the right-hand side, of 1,500 megawatts online by 2025 and 3,000 megawatts by 2030. But really importantly, it's worth highlighting, when we developed the storage roadmap for the state and developed the 3,000 megawatt target, that was based on the top left, looking like a 50% renewable electricity target by 2030. It was not considering the need to fully decarbonize the system. And so the modeling that we have seen, and that's come through the New York Independent Systems Operator, is multiple times more than 3,000 megawatts ultimately being needed on the system. So let's go ahead and advance to the next slide. And I'm going to round this out with just talking a little bit about what NYSERDA has been doing. And this is a large driving force of the types of installations that you will see coming your way in many of the communities throughout the state. So we basically think of storage in 2 ways. There's retail storage, which for our nomenclature, that's any project that's less than 5 megawatts in size. The real magic behind that is that's what's covered within the standard interconnect requirement at the investor-owned utilities in the state, regulated through the Department of Public Service. To date, and I'm going to talk a little bit more on the next slide, those incentives have been fully allocated everywhere except for Long Island and in Con Edison's territory. So the only additional, what we call retail incentives that I anticipate will be coming out would be for residential storage when it's paired with solar. Right now, that incentive is available in Long Island. I do expect that NYSERDA will be expanding that elsewhere within the state. Bulk storage, which is projects over 5 megawatts. These are the really large projects consuming, taking up acres of space, generally in special purpose buildings or 40-foot shipping containers that look like a tractor trailer. Comparing that to the retail storage projects where you're literally looking at something for a residence that looks like a third of a refrigerator that might be bolted to the wall, to a commercial installation, which again could be tens of thousands of square feet, but again in either a special purpose building or in 5 to 6 of those 40-foot shipping containers. Stan's going to actually have some slides that show exactly what those systems look like. On the next slide, I did want to show, this is the projects that the use cases that storage is actually providing. And so I'll take a minute just to explain some of these. The first couple are pretty important. So historically, the grid has been built out, the generation, the transmission lines that you see overhead, the distribution system, it's been built to accommodate the single highest load throughout the entire year. That's generally happened on a July or August day after multiple days of 90-degree heat, and it's generally caused by air conditioning load. And so what's wound up happening is ratepayers, so every one of us on this call, we're paying for that system and for the reliability that's required for that system, even though it's, if you were to think about it in terms of the number of hours of the year that you need that much load, it's a few hours that you need it all. And most of the time, we're operating at about half the capacity of what the system can provide. So that's equivalent of if we were to, say, have 12 lanes on the Thruway or the Long Island Expressway or the Northway or wherever you're located in the state to accommodate the 3 busiest holidays of the year. And all the rest of the year, that infrastructure is maintained and it's paid for and it's sitting there. That, in effect, is the only way the system could have been built in the past. So the ability to have renewables and energy storage is starting to change that paradigm, and it's helping to provide alternatives to simply building out the system to meet those peak periods. That especially becomes critical as you look downstate. Just like the traffic gets worse downstate, there are constraints that prevent any electricity during the busiest times of effectively getting into some of the major load pockets without constraints. And that drives up price, and that also drives up the need for additional infrastructure. And I'm not suggesting that storage and renewables will fully address the need for any of that, but it does serve a very mitigating role to the need to continue to build additional infrastructure. The third bullet, the other thing that it does is this fancy term of ancillary services. In effect, that's the grid reliability. That's giving confidence that when you plug something in at your house, the correct voltage and the correct hertz are coming out so that you're not damaging equipment. So historically, that's something that had been largely done through fossil plants that were ramped up and ramped down. Storage actually does a really good job at providing that response near instantaneously. And then finally, the last 2 bullets, I mentioned earlier on integrating solar and wind so that it's available when we need it. But then finally, you're likely to see installations that are being proposed either in homes or in businesses for what could vary from either their electric bill management, so they want to charge the batteries or storage when it's nighttime and the costs are less, and then discharge it during the day so their electric bill is less, or obviously for backup power. And if we could move to the final slide, this is a representation of the storage that we had deployed in the state outside of pumped hydro back in October, so we're a bit higher than that now. And again, the larger the circles, the larger the number of megawatts are in that location. But take this as indicative. It really is reflected throughout the state. And if you look on the bottom half, what I wanted to highlight is there is just over 1,000 megawatts of energy storage that is contracted. So these are firm projects that NYSERDA has contracted for, or a utility has contracted for, that are in varying stages of being going through permitting and public comment and trying to get the project built. And so just to put a number with that, that reflects about 100 large projects, what we would call large commercial or bulk projects, but then it's also hundreds of residential projects. And again, I expect that number will actually continue to get larger. Now it is my great pleasure to hand the mic over to Stan Whittingham. And I will say, just on a personal note, it's probably been about a dozen years since I had met Stan. And he not only is one of the most brilliant people that I have had the pleasure to work with, but he's also one of the nicest human beings and individuals. And so we are so blessed to not only have Stan here at one of our great SUNY institutions, but also for him to generously give of his time this evening. And with that, Stan, I will turn the mic over to you. Thank you.
Thank you very much, Jason, for those kind words. If we could go to the next slide. What I want to do initially is discuss what storage is, then the different sorts of storage, then I'll get into batteries and some of the issues you're probably interested in. So we want electrical energy, and as Jason described, the amount we want varies throughout the day, so we need to store it for use. And any energy storage system is a means of holding energy in one form and then converting it to another form. So if we want to get electrical energy, then we can initially hold it as kinetic, potential, chemical, or some other sorts of energy. And you're all familiar, I think, with all the different storage types. So we have chemical energy. This is what we can store in a battery, a fuel cell. This is what's in your gasoline or coal. You burn it, so it's not rechargeable. So I put in red there. And I say dirty fuels. Then we have potential energy we use, and this is pumped hydro. And also straight hydro, as we have in certain parts of the state, and Quebec has a lot of it, where we're using clean water as a means of renewable energy. Then we have kinetic energy, and this is a flywheel, and I show you a flywheel on all the way on the right-hand side. This is at Beacon Power near Albany. Expensive and probably not commercially viable. It's making money now just because the initial company went bankrupt. For clean energy, when we talk about kinetic, we're talking about wind and windmills, or we're talking about tides in certain parts of the world. Then we can also store energy as thermal energy, let the sun heat up water or rocks. And renewable energy there is using geothermal energy, which is used in the West quite a lot. And clearly we can also use sun for thermal energy to heat systems up. If we go to the next slide, and really of all those systems, there's just two we really need to discuss. They're by far the most dominant. One is pumped hydro. So we convert potential to electrical energy. We're talking about gigawatt hours of energy there, and I'll come back to that in a moment. These are now highly efficient. So I expect most of the systems in York have been upgraded with new turbines. So you're talking about 73% efficiency. But there's very limited future development because new sites aren't available and the environmentalists don't exactly like us building ponds. So by far the most flexible are batteries. Here we're going to convert chemical energy to electrical energy. They're extremely flexible, they're common. I think everybody on this call probably has one on their person now, maybe two or three. So if you have a phone, a watch, a computer, you've got a battery in it. So these can be portable or stationary. They can go from milliwatts to gigawatts, and they're very quick to switch on and off, fractions of a second, unlike pump hydro where you're talking a few minutes. So you're familiar with smartphones. They use just a few watts in them. And on the right-hand side, I show you probably the world's largest battery storage facility. This is in Moss Landing, California. This is 1.2 gigawatt hours. So let me explain. This is a 300 megawatt system that can generate 300 megawatts for 4 hours. So you see terminology used either as megawatts or megawatt hours. So this particular one is a very cost-effective system. It replaced a gas-fired plant. So it's actually got all the utility infrastructure already there. So that building is full of lithium-ion batteries. And these are more in these containers that Jason was mentioning. So let's go to the next slide. And I'll very briefly describe what a battery is. No chemistry. I promise not to do any of that. If you look at any battery, it really has three active components. An anode, which in the case of a lithium battery is where you store the lithium when it's fully charged. A cathode, where the lithium ions go to when you discharge it. Then between them, an electrolyte, and it's the ions that migrate through the electrolyte with their charge on, and the electrons go through that external circuit and do works that I've shown by that letter A. So that's essentially every battery is that way. Then you have typically a plastic casing to hold the whole thing. The electrolyte in essentially all today's batteries is a liquid. In the case of some of them, and I'll show you some examples in the next slide, this may be water, but for all the lithium-ion batteries, those you're going to use for energy storage, this is organic liquid. And today, this is the component that can catch fire and burn. So let's go to the next slide. So let's do a brief history of batteries. I think most of you are familiar with the three I'm going to describe. The very first battery was discovered by Volta in Italy in 1799. And this is a temple built in his honor. It's so-so on the inside, but if you walk around to the back, this beautiful view of the lake and the Alps with snow on in the middle of July. This is the battery that probably many of you made in school, probably in grade school, putting zinc and nickel together, and you can generate a potential. No, never commercially used. The most important battery was the one invented in 1859. That's the lead acid battery, the one you still have in your car today. Obviously, it's somewhat better now, but that battery has been around, as you can see, for a very long time. The other battery you're all familiar with now is the common alkaline cell. This was first marketed in the 1960s. This is what we know as a primary cell. You can't recharge it. Well, let me say you shouldn't recharge it. It may blow up if you do. But these are primary cells. They just cost a few cents. Then the rechargeable lithium-ion battery was invented in 1972. And I show you a picture of one of the first ones on the right-hand side. You can see a battery connected to a little solar cell and then a watch. And this particular one still sits on my desk. It still works. The watch part isn't in all that great a shape, but the battery is still working. So a well-made lithium-ion battery will last, I won't say forever, but this one's over 45 years old and still going. But it took till 1991 for commercial success. The number of lithium-ion batteries marketed prior to that. But it was Sony with a vertically integrated business plan that developed the lithium-ion battery and used it in their devices. these lithium-ion batteries now dominate the energy storage market, the rechargeable market, except for your starting, lighting, ignition in your cars, and for uninterruptible power supplies. These still tend to use lead-acid batteries. You will not see any lead-acid batteries of any significant size used for large-scale energy storage these days. So let's go to the next slide and explain why lithium-ion has taken over. Lithium-ion stores the most energy per unit weight or volume. So that's why it's very important in small devices, smartphones, watches, your laptops, because you want to get as much energy in as little volume as possible. And this is why it also dominates in electric vehicles. They're essentially minimal maintenance cost. So they're computer monitored, and I'll again get into that in a moment. So they're totally unsealed, like some of the other batteries, lead acid. They're sealed now, but they didn't used to be. They're very large maintenance cost. And some of the original hybrid electric vehicle buses had lead acid batteries on them, and they were a nightmare to maintain. So everyone's much happier with lithium ion. So you can monitor them remotely and look after them. They are also readily available. So there are billions made per year. And the real challenge we have these days is probably 70 to 80% of those are made in Asia. Another key factor in their favor is cost is dropping all the time. It's going down 5 or 10% every year. And it's gone from over $2,000 a kilowatt hour to under $100 a kilowatt hour now in large quantities. And another thing that utilities like, they're portable. What I mean by that, utilities can move them as directed, because they're typically in shipping containers, towed and moved somewhere else. And I think there's a picture of the system in Binghamton. Was here for several years. Now it's in Ohio because they make more money. On the downside for lithium-ion batteries, they need electronic protection from overcharge and discharge. So every cell has electronic protection in them, which adds up on the cost. If they're not protected, then you can get thermal runaway. If you get thermal runaway and don't control it, it can result in fires. So every lithium-ion battery has to have a very good battery management system. And I always emphasize this, and folks say, well, I can get a cheap replacement battery for my phone or laptop from China. I tell them, don't do it. There's a good chance the electronic protection is missing. The other thing in lithium-ion batteries, like they're just like us, and they want temperature control. So they get unhappy below the freezing point and above about 90 to 100 degrees Fahrenheit. So large systems are in air-conditioned containers. And I'll get back to that in a few moments. So if you're worried about how they're being used, just think about if you are going to be comfortable, they'll be comfortable. Now, go back one slide, please. Okay. So there are two types of lithium-ion batteries you're likely to meet. One you may see described as LFP. This is phosphates. These are lower cost, they're safer, but they store less energy per unit volume or weight. So you won't find those in your phones or in high-end cars. They're dominant in China, and I expect them to eventually dominate in the US for large-scale battery energy storage systems, where weight and volume isn't such an issue. And by the end of this year, we'll have them manufactured right here in New York State in Endicott by IM3 New York. The other system you're likely to meet, and again, these will be in grid storage today. These are the oxides. You'll see them maybe described as NMC or NCA. This means nickel, manganese, cobalt, and the A stands for aluminum. These are dominant for portable devices, as they have the highest energy per unit volume. And these are dominant today for battery energy storage in the US. But I expect that to change. Let's go to the next slide and see what a battery actually looks like. So any battery is made up of a number of cells. So in your car, you've got a 12-volt battery. This comprises 6 2-volt lead acid cells connected together. And I show you here a picture of typically cylindrical cells connected up and placed into modules. And this is how the buses go in most of the grid storage. These modules are then placed into racks. We have, as I mentioned earlier, battery management systems that controls these operation of these batteries, and they monitor the temperature, the pressure, and the environment within the containers. So they should be totally safe. And then we have a balance of system equipment, the DC to DC conversion, and so on. So let's go to the next slide and just look at some of the different ones we might see. So here are 3 different installation types you typically might meet. On the left-hand side is the typical Tesla wall system. This is a kilowatt hour or so. Commercially, you're going to find systems from a few kilowatt hours up to, say, a megawatt hour. So those shipping containers have 2 to 4 megawatt hours inside them. And then you have utility scale, which go from megawatt hours up to, I showed you earlier, gigawatt hours. So you have these total difference in systems. Looking at that one on the right-hand side, look on the roof there, and you'll see the air conditioning units on top. So this is what you need inside those systems to keep them nice and cool. And both Jason and I can tell you, we went to visit this particular one on a hot summer day. It was about 90 degrees outside, and it was very pleasant walking inside where it was 72 degrees. So this is what these batteries like. Let's go to the next slide and let me start discussing some of the, I call it fake news these days, or rumors and so on, that lithium-ion batteries don't last long. They can last up to 10 or 20 years. The longer they last, the more expensive they're going to be. So you're not going to get a 20-year battery put in your iPhone because Apple knows you're going to replace it in 2 or 3 years. So the battery is designed for a 2 or 3 year lifetime. But the utilities are expecting at least 15 to 20 years. You get about a 10-year warranty on your electric vehicle. The second issue people have is, well, will they work in New York's climate? The answer is yes, they will. But again, they need some of the same conditions we do. They need shelter, they need temperature regulation, and so on. So look after them, and there's no issue. You hear about range issue in electric vehicles. That's because as soon as you get in your car in the morning, you'll turn on the defroster, you'll turn on the heater, and that energy comes from the battery, which you don't use in the summer. The other fiction is these batteries can't be disposed of safely. Recycling is required. I think by New York state law, you cannot toss any battery out into the garbage. It'll be the normal, and it's already happening in New York State. There's a large facility at the Kodak area in Rochester, New York, run by Lithium Cycle. So they're recycling lithium batteries today as we talk. And battery energy storage will not end up in municipal waste streams, and definitely should not end up in recycling facilities where they can get crushed and cause problems. The other fiction is you only need these, or they're only appropriate in dense population centers. I think you can almost say the opposite. If you're living in a remote place where the grid is unstable, you need them everywhere. But they are important for resilience. We would not have had so many issues with the hurricane in New York City had there been more storage there. As Jason mentioned, they be used to stabilize the grid, and they're very important to eliminate these expensive, dirty peaker plants. And they enable the integration of renewable energy such as the sun and wind, which tend to blow and shine when they feel like it, not particularly when we need to use them. And the bottom picture there, I think, is the picture of the facility that was in Binghamton, New York, next to the coal power plant. My understanding is they turned that facility on. Within a month, the coal power plant was turned off and never came back on again. AES, who owned that facility, eventually moved it to Ohio because it had more demand there. But that's why they're liked by utilities, they're flexible. Let's go to the next slide. Lithium batteries are not normally cheaply made. There are some that are cheaply made and some that are fake. You're not going to, I think, see those. If you're building a large facility, you're going to go to reliable manufacturers. So you have to be very careful. Don't go to the lowest cost bidder. Make sure you know where they're coming from. Bad systems, badly designed systems can catch fire. And Samsung saw that in their phones. And we know why that happened now. Boeing had some systems there. Again, bad designs, and I think those companies have learned and everyone's learned from them. So we have had advances in the technology and the safety standards, and there are very strict fire and building codes that will mitigate fire safety risks. As I already mentioned, you've got to buy from reliable sources, not just the lowest cost. And there are codes that have to be complied with. There are concerns there are not adequate safety standards in place for these systems. I think that's not true. They have changed with the time as we've learned. And the systems eyes, and certainly New York State has those codes in place to protect everybody. The other fiction that I know a lot of us thought this was crazy when they first did it, but you can use water and you should use water. And I think you'll find that all the stewardesses on airlines have been told if they have a problem with a laptop or something or phone overheating, what you do is drop it in ice water, you cool it. But water is now the standard means of extinguishing a lithium-ion fire. The main thing is to cool it down. And I should point out, lithium-ion batteries should not contain any metallic lithium. That's why they're known as lithium-ion. There's only lithium ions there, no lithium metal. The key thing is people have tested water, demonstrated it, it's useful. The essential part there is that fire folks have to be trained as to how to handle such fires. And I think most of the facilities that I've seen in New York State, the local fire departments are extremely well trained, and they train every new person coming on board. And I'll go to the next slide, which I think is my last slide. That these systems unmonitored couldn't be further from the truth. They're extremely well monitored. We got a kind of sly comment when we said, what's the largest cost of looking after these systems when we visited this facility? And their comment was mowing the grass, because they can monitor the system continuously with a computer remotely. The computer can tell them immediately if something's going wrong and shut down the system. So this is where you need a good battery management system. You'll see this described as BMS. So this will keep everybody appraised of what's going on. And I think I already discussed the need for first responders and firefighters are now fully prepared to respond to an accident involving energy storage. And I'll say the biggest danger from energy storage or electric vehicles, probably not the batteries themselves, but electrical hazards if you have to cut into them and there's very high voltages in there. So there are specific training now given to all these folks, so they should be comfortable handling it and not do anything, I say reckless, as what happened in the Phoenix, Arizona case where they had no training at all. So I'll switch back to my NYSERDA folks with the next slide. Thank you very much.
Thank you so much, Stan. Next slide. Perfect. Thank you. And so one remaining slide covering a few of the concerns that we hear, from our work with communities across New York State. And those are regarding some of the more environmental concerns. So the first one regards the fact that battery energy storage systems will pollute the environment, or that if firefighters were to use water on a lithium-ion energy storage system in the event of an incident, that will produce some kind of toxic runoff. As I mentioned, or as Stan mentioned earlier, pretty comprehensive testing has been done to show that water is a suitable substance for cooling off and extinguishing lithium-ion battery incidents, which actually minimizes the need for firefighters to be utilizing spray foams and gels, which are known to contain some of the most harmful chemicals that many people across the country and across New York State are particularly concerned about getting into the ecosystem, such as hydrofluorocarbons or PFAS. And so because you're already not going to be utilizing those flame retardants or firefighting substances, you're already in a good place there. And many other types of fires, just in a similar way to a lithium-ion battery fire, depending on the nature of the incident, first responders may need to utilize some types of fire water collection strategies, but these are not issues or concerns that are specific to battery energy storage systems. These are trainings and techniques that are already in place by firefighters when responding to industrial or chemical incidents. Another concern that we hear is that batteries produce toxic gases and will negatively affect air quality in communities. In fact, lithium-ion battery energy storage systems do not off-gas or produce emissions during operations the way some other electrochemical batteries do. And finally, the concern is that these batteries will produce excess noise in operation. And again, for larger installations, really the only noise that you're going to be concerned about is going to be the noise coming from HVAC systems and inverters. There's no other noise that will be given off based on the batteries during operations. And appropriate siting measures can ensure that noise will not become an issue for project neighbors. What I mean there is referring to things like noise requirements or setbacks or other requirements that can be put in place by a local government. And that covers the fact versus fiction here. What I would like to just note is that, again, this is part 1 of 5 of a webinar series, and we'll be addressing some of the concerns raised in this fact versus fiction section in more depth during these the other sessions, including in this webinar series, including questions about decommissioning and end-of-life considerations, as well as the fire safety component. Next slide, please. And the only last thing before we get to a facilitated Q&A with Dr. Whittingham and Jason, I just want to give a quick overview of NYSERDA's battery energy storage system resources for local governments. Many of the communities here on the webinar tonight may be familiar with NYSERDA's Clean Energy Siting Team or our Solar Guidebook for local governments. And you can think of this as the younger sibling to that Solar Guidebook. So back in 2019, we created the Battery Energy Storage System Guidebook as a way of getting municipalities the tools that they need to prepare for battery energy storage system development. And so contained in this guidebook are 3 primary things, or actually 4 primary things. Number 1, there's a model zoning law, which can be customized by the municipality to ensure that they have adequate regulations on the books for battery energy storage systems. From there, we have a model permit and an inspection checklist, which can be used for small residential and commercial battery energy storage systems to create a streamlined process for the installation and permitting of these systems. Very similar to the Unified Solar Permit, which has been adopted by hundreds of municipalities across the state of New York. And finally, the final section of the guidebook is a clipping of all of the relevant provisions within the 2020 New York State Fire Prevention and Building Code, which was implemented as of May 2020 to include chapters on battery energy storage systems. That includes code references that are in the residential code for residential energy storage systems, up through the fire code for large-scale battery energy storage systems. So this section of the guidebook contains all of those code references. And finally, just kind of end with, the clean energy siting team's offer, which is to say that we are here to work one-on-one with municipal boards and local officials to provide free technical assistance, answer questions, host trainings, things of that ilk. We do offer a couple of accredited trainings for code enforcement officials or planning and zoning board members, which are accredited through the Department of State's Division of Local Government Services and the Building Standards and Codes Office as well. From there, if you wouldn't mind going to the next slide, please, and we'll take just a minute to finish aggregating some of the questions. Thank you guys all so much for submitting questions through the Q&A. Please feel free to do so. We will do our best to get through to those questions. So give us just a minute to get those together, and we'll hop back on with a Q&A with Jason and Dr. Whittingham. All right, Jason, are you able to rejoin us here? We've got a couple of questions that I'll throw your way.
Yes, go for it, sir.
All right, thanks, Jason. So the first question which came in was just wanting to confirm, when we're talking about the capacity in terms of megawatts of these systems, does it assume a 4-hour capacity insofar as a 5 megawatt system at 4 hours of capacity would be 20 megawatt hours? Would you mind clarifying that, please?
Yeah, it's a good question. Thank you for the question. So most often what you will see is generally around 4 hours. There's a couple of reasons for that, but they really go, the reasons really center around the amount of revenue that project can make on the electric system. And you'll see some cases for something like frequency regulation where it would be up to an hour of duration, but most often they're around 4 to 6 hours. There are definitely needs that we've seen will likely start to arise as we get to higher and higher levels of renewable penetration for longer duration storage. And I would let Stan touch upon when other types of solutions might start to become a more viable choice from lithium-ion. But the other thing that I will point out is you're generally limited by just one thing. So you have the megawatt hours, and then you have the megawatts. And again, let's say it's a 100 megawatt system and it's 400 megawatt hours. So for 4 hours, you can discharge that more slowly. So you could discharge it, say, for 50 megawatts over 8 hours. The big limiting factor is generally the battery chemistry or the power electronics that will limit how many megawatts you can actually push out at once.
All right, thank you, Jason. Jason, one other question, we'll stick with you right here. We had a question early on regarding that map that we had showing the deployment and some of the pipeline for energy storage in the state of New York. We just wanted to clarify for the figure as of October 31st, 2020, which demonstrates installation of about 96.5 megawatts of energy storage. Does that primarily represent retail-sized projects? And are those primarily on the customer side of the meter? Would you mind just clarifying what is comprising that figure?
Yeah, absolutely. If I did my math right, it's somewhere between 32 and 40 megawatts of that is what we would call bulk storage. So the rest of it would be customer side of the meter, either residential installations or a commercial installation.
Perfect. Thank you very much, Jason. Stan, we have a question for you here. Wondering if the types of electric vehicles that we're seeing, or the types of batteries rather in electric vehicles these days, are these typically going to be the phosphate batteries, the LSPs, or would you mind clarifying what type we're seeing in EVs?
Yeah, for the EVs, they're all the nickel, manganese, cobalt, what we call the layered oxides. Not the LFP. There's far as I know, there's no LFP-powered electric vehicles in the US. China uses mostly LFP. Tesla is shipping their cars from China to Germany with LFP in them. But some of the high-end cars are all going to have oxides. If you want a lower cost car, like let's say $25,000, Tesla is going to start using LFP in a few years' time. But there's no real facility making LFP in the United States at this time. So it's layered oxides at the moment.
Perfect, thank you. Another one for Dr. Whittingham. Would you mind describing the current process that is being used to recycle lithium-ion batteries without getting into anyone's proprietary processes? But an idea would be great.
If they're proprietary, I wouldn't know about them, right? See, folks like Apple have robots to pull their phones apart and take all the components out. The typical method is you'll get the batteries, the smallish ones, and then grind them up in an inert atmosphere so they don't catch fire, and then separate it out into the active components and the inactive, and the active components are then turned into what they call black mass, then recycled into making new batteries. And that includes all the copper foil in there, which is quite expensive. And that's, I think, the way the folks in Rochester are going to use. But there's 3 or 4 different ways. Some folks are talking about scraping the material off and using it directly. Others are going to burn it, and that's where it gets messy because there are fluorides in there, and if you burn it, you may get some PFAS into the incinerator. So there's a whole range of different methods being used, and it depends a lot on where the source of the batteries come from. So in a manufacturing plant, 5 to 10% of the material is waste. That's very good material, and they can do that in a very high-end manner. A battery that's been used, say, for 15, 20 years is less useful, and they're going to tend to turn that into a metal-rich material for future use.
Perfect, thank you. And while we're on the question of recycling, I see that we have another question asking if there are any existing recycling programs in place for batteries from large-scale facilities, with a specific question about whether the Life Cycle Recycling Center, which is the project in Rochester that you describe, whether they would be able to handle volumes of batteries from these large-scale energy storage facilities once they become obsolete or non-functional. Now, real quick, Stan, before I turn that question to you, I do just want to note that, again, event number 4 in this webinar series will center on decommissioning and end-of-life considerations. And we will actually, we're very pleased to announce that we will have a representative of Lifecycle, that energy storage recycler in Rochester, joining us for that webinar. And so that would be another great time for them to sort of explain their process and maybe answer some of the questions that you may have about their process. But Stan, any thoughts about whether there are existing recycling facilities capable of handling a large-scale installation's batteries at end of life, or whether that's still developing?
No, the facility in Rochester, I think they'd be extremely happy if they could get that size of input into it. The issue now is collecting the batteries to, as it were, to give the input to the facility. So, because most of the electric vehicles, they've been on the road maybe the oldest 10 years, so they're just starting to be recycled. They're probably collecting mostly phones and computers and things like that. But if they could have some large-scale facilities, they'd be more than happy to do it. That's what they really need to make it economically viable. So I don't think there's any challenge there. The only slight challenge may be getting the old batteries to the facility, because I think they will be determined to be a hazardous cargo. So if you're going to, for example, recycle the batteries in your car, the best way of doing it is actually take the car to the recycling plant, and then it's just a regular cargo, and then take the batteries out of the recycling plant.
Perfect, thank you. We had one question that I just want to speak to and clarify real quick, a brief question about the inclusion of energy storage systems in the New York State building and fire codes. And I touched on this briefly before, and we will talk more about this in the zoning and permitting webinar number 3 in this series. But the 2020 New York State Uniform Code, when that code cycle was adopted last May, it was adopted to include regulations for everything from residential through commercial battery energy storage systems. What that means, since it's part of the Uniform Code, is that it's automatically applicable in most jurisdictions in New York State outside of, I believe, New York City. And so there are, certain protections and requirements for these energy storage installations which are already in place without the need for local adoption. And if that is a topic you're interested in, we will see you for webinar number 3 on zoning and permitting. We also have another question for Stan. Would you be able to comment on the status of solid state batteries and how they differ from the technologies that we've described tonight, the lithium-ion batteries?
Yeah, so solid state batteries have a solid electrolyte in the middle instead of the liquid that I described. There's only one such battery commercially made today, and that's made by Blue Solutions in France. It's used in some of the Mercedes buses, it's also used for grid storage. It's a relatively low energy density, as far as I know, totally reliable, but it operates around 70 degrees centigrade. So it's not suitable for your personal systems. The advantage of a solid state, you do not have to control the temperature in the environment like you do for the liquid ones. So if they overheat by 30 or 40 degrees, they'll probably work even better. So no, once they can get them operating closer to room temperature so we can all use them, it'll be good, but there's a lot of research still to be done to make that viable. In scientific terms, it means you've got two solids together. It's difficult to get ions across that interface. So that's what has to be solved. But a lot of research is going on. Probably be initially quite a lot more expensive until they start making them in the millions and billions. But that's the hope of researchers in the next, say, 10 years. You won't see them much before 10 years, I think.
Perfect. Thank you, Stan. We got another question asking whether homeowners should worry about the kilowatt-hour sized systems for fire. I would just note again that we've covered that the New York State Residential Code, which was updated in 2020, it does include a number of provisions which are really explicitly designed to mitigate the fire risk of residential energy storage systems, including size and separation requirements, meaning they can't go over a certain size and they have to be a certain distance from each other. There are also things like fire detection and smoke detection requirements, as well as protection from vehicular impact if it's going to be a system placed in the garage, and other specific protections like that. So again, there are requirements that are already in place in most jurisdictions in New York State to ensure the mitigation of risks of residential energy storage systems. Now, Stan, another question for you. In the event of a runaway fire or thermal runaway, do lithium batteries have a risk of explosion, or is it more of a slow burn?
It's more of, I would say, a consistent slow burn. So when I teach my students about these fires, I show them two pictures. One's a Tesla burning and one's a Nissan sports car burning. And I ask them which is which, and you can't tell any difference. So normally it burns just like gasoline. They don't normally explode. There's a bigger danger from lead acid batteries from exploding if you get hydrogen generated in them. But it's very unusual for any explosion with lithium-ion batteries. They all burn. And if you've got a Tesla, it gives you about 10 minutes to get out of the car before there's any serious hazard there. So it's very unusual to have a sudden explosion.
The one thing I will add, and we'll touch more on this on the fire safety webinar, is what you don't want to do with a large containerized type system is not have good management and gas detection that keeps the system essentially sealed, because that is when you can get explosion risk. That's what happened in Arizona, and the requirements around managing thermal propagation and the risk of explosion would include things like sensing for the gases that are released, ventilating, and making sure you don't build up an environment that could explode.
Yeah, and Jason, to that point, there was another question that was asking, what are some of the hazard mitigation systems used by the battery management system and or first responders? And I think you kind of introduced a couple of the key components right there, right? So you have not only sensors for, gas buildup or pressure buildup. There are also sprinklers that, in some systems will have installed. There's also what is known as deflagration venting sometimes installed, which means that once the pressure builds up to a certain point inside of the container, it will blow the panels to ensure that that pressure cannot continue to build up in the event of an explosion being imminent or something like that. And I would just say that we definitely will be covering some of those more specific systems and requirements in the fire safety webinar with a couple of experts who really know what they're talking about there. So would definitely recommend
and then
that.
As Stan mentioned earlier, there also are fuses that will disconnect, and if it's not controlled, stop charging the system, stop discharging the system.
Perfect. Thank you both. One more question for Stan here, and I say one more. There's plenty more, so maybe don't take my word for that. A question about the growing concern about lithium supplies globally and how they will, whether they'll be able to meet growing demand for lithium-ion batteries, and also concern about geopolitical implications in regard to lithium mining and procurement.
I could answer that and say lithium's the same as cobalt, maybe the same as nickel. They're all on this special list that the federal government has that we need supplies. There's plenty of lithium in the world, certainly for the next 10 or so years. Then after that, we're going to start recycling a lot from cars. So when I got into this business, all lithium came from North Carolina. So if you look up any lithium company, the headquarters is still probably in Charlotte. Then they discovered the cheap lithium in South America and these brines. And it's just a matter of ramping up production. It takes about 2 years to produce lithium from brine. So it's the longest process. So the prices tend to go up as the demand goes up, and then they'll drop as a new plant comes online. No one believes there's really an issue of lithium supply and demand, certainly for the next 10 or 15 years. And by then, I expect we may have different systems.
Perfect, thank you. Question for Jason here. Just asking, what are the best locations for battery energy storage systems in New York State? Where in the state are we really seeing these systems crop up, and where is the state and or utilities looking to develop systems?
So I'm going to answer the question from a non-residential standpoint. So by and large, from a system that's charging from the grid and discharging into the grid, the utility might procure it, or a company might put it in place to sell directly into the wholesale market. And that's the majority of the megawatts or megawatt hours that you'll see. So there are, by and large, it's as you get down towards the lower Hudson Valley, New York City, and Long Island, where the prices are the most advantageous for using that storage to actually discharge onto the grid during peak times, and then also receiving what's called the capacity payment. It's basically a reservation payment that you will be there. There are certainly exceptions to that. There are pockets in the north and western part of the state where there are grid constraints, where it makes sense to have the storage really co-located with large-scale wind or solar. And then there are also, I know this was another question coming up, are places, particularly within some of National Grid's territory and New York State Electric and Gas, where just because of the infrastructure, think like the Adirondack Park is a good example. The utility has done what they can do to firm up the grid architecture. And there's a lot of power outages because of storms. And in those cases, National Grid's a good example. They're procuring I think it's a 5 to 10 megawatt 4-hour duration system to help with some of that. And the one thing I'll just add, finally, there is a limited duration, of course. So generally, there's a balance and a compromise that has to be struck with how much resiliency you want and what you're willing to really pay for, and what the restoration times would look like.
Great. Thank you, Jason. Got a question, I think that, either Jason or Dr. Whittingham, whoever feels so inclined. One of the fact versus fiction slides mentions the lifespan of lithium-ion batteries as potentially 10 to 20 years, depending on use, of course. Is that lifespan defined above or based on a certain capacity? So are you saying that it's going to be, at 50 or 60 or 70% capacity by the time you get to that 20-year threshold? What are we thinking about there?
I think you have to talk to those folks making the batteries and giving you those warranties. The grid application can be just a few percent up and down. It could be 60 or 70% each day. So it depends on the specific application. Look at your own uses. If you got an iWatch, you probably deep discharge it every day. If you got a laptop computer like me, it's probably plugged in most of the time. So it depends on the specific application. And I expect the long warranties being given out are based on not full deep discharge every day, 50%, 60% at most. And certainly the software will not let you go to the last 10% either side. That's built in there. So you can't overcharge, you can't over discharge.
And what you'll see more often than not is there's an operations and maintenance contract that's bundled in to the price of the storage, depending on what the use case is, like Stan said. So when people will say it's a 20-year asset life, which is generally what the utilities think of it is, that's not to imply that those same battery cells are lasting for 20 years. They will be swapping out modules and racks throughout the course of that time. Stan, is it still a rule of thumb that EVs are generally designed to get to about 80% remaining discharge before they're considered at their no longer meeting their specs?
Yeah, so if you buy a new EV, you'll probably only use the middle 50, 60% of the battery. So that by the end of the 10 years, you're still getting the same amount of energy output, now using 80 and 90% of the battery.
All right, perfect. And next question is for Stan. We're going to highlight again another type of battery that we didn't really address in this presentation. Would you mind speaking to the future of flow batteries in the United States? Is this an industry that we could see either supplanting or joining the market share of lithium-ion batteries in the near future or the extended future? Also, if you want to explain exactly what a flow battery is, that would probably also be useful.
Yes. So a flow battery basically separates the electrochemical part of it from the fuel and the oxidant. So typical ones used are vanadium redox. There was one used commercially in Utah. They store the chemicals in large tanks, then have the electrochemical, the battery part, you think about it, separate from that. They're basically like a chemical facility. They're not mobile. So they used it for several years there, and then it's just that rusting. The big challenge flow batteries have is dollars and cents. How much is it going to cost, and can the price get down to that of a lithium-ion battery? But if you want a system that can operate, say, for 24 hours at a fairly low output, you can have very large tanks of the chemicals and this fairly small battery in the middle of it. So they have advantages. The challenge of any new system coming in is the dollars per kilowatt hour that lithium ion is costing now. But if you're talking about long storage, you can look at a large flow battery in principle, almost like pumped hydro, but using chemicals and electrochemical cell in there. So in the end, it's going to be dollars and cents, and they're going to have maintenance costs because you can have pumps moving things around up and down and so on. So they're going to have to be much better than the lithium-ion battery or much lower cost to break into the market.
Perfect. Thank you, Stan. Let's see here. Got a question about where do we suggest municipalities and more specifically fire departments go to get specific training for dealing with a lithium-ion fire possibility? And a couple of pieces here before. I mean, largely I'll say that we'll definitely cover a lot of the incident response and firefighter piece in the next webinar. But a couple things I do want to highlight here. Number one, one of the main considerations when it comes to the fire risks of the system is safe installation practices and codes compliance. And to that end, like I said earlier, the NYSERDA's Clean Energy Siting Team, we do have a training developed, which is accredited with DOS, Division of Building Standards and Codes, which will train your fire marshals and code enforcement officials on everything that they need to know regarding the fire code compliance for energy storage systems. In addition, 2 weeks from now, on our fire safety webinar, we will be joined by a representative of the New York State Office of Fire Prevention and Control, the OFPC, and they will, definitely be the authority to put together training on energy storage systems. So I would suggest anyone with those kind of questions, if you're able to, please do participate in our webinar 2 weeks from now. We'd be glad to have you there. We got another question. Saying solar energy in the wintertime is minimal, so there's very little to store. Is solar not viable for reliable electricity in New York in the wintertime? Jason, would you like to take that one?
Yeah, I'll give that a shot and would be happy to follow up with anybody because we actually do have some real metrics on what the performance looks like. It is not as impacted as you might think. Obviously, the hours of sunlight are significantly different in the winter. However, the generation on a clear day is still going to be pretty good. A lot of the systems that are coming out now are what's called bifacial. So the front and the back of the glass is actually used to help generate electrons. That helps a bit more with the efficiency. But the other reality I think that we just have to keep aware of is I mentioned historically that air conditioning load today is what's really driving the load. So it's a summertime peak. That is expected to start shifting towards a winter peak as there is more and more electrification. And so I think there's clearly a role that solar will play. And I think that one of the things that solar and wind, including offshore wind, do nicely is they balance each other from daytime to nighttime.
Perfect. Thank you, Jason. Question for Dr. Whittingham. Question just about the future of lithium-ion battery development. Where do you see lithium-ion research focusing on in the next 5 to 10 years? Another way of phrasing that question, what are you and your colleagues at SUNY Binghamton working on these days?
So we're working on better materials, safer materials, and we're supported by the US Department of Energy. And their goal is to basically double the energy density of today's batteries. So we calculate what the theoretical amount of energy is. What we're getting out today is about 25% of that. So our goal is to get to 50%. And the main project there is battery 500. The goal is 500 watt hours per kilogram. It'll use, I would say, essentially the same materials, but not quite the same materials as we're using today. And the big push is to get all the cobalt out of the batteries. Cobalt is the most expensive component, and it uses child labor, and the Chinese probably dominate 90% of the market for the cobalt, and we don't want to be beholden to any one country. So the materials aren't going to change dramatically, but we're going to make them better. So we mentioned earlier, solid state is going to be something in 10 years out. But that, unless somebody comes in with a great new material, you're not going to see anything dramatically different.
Perfect, thank you. As you guys can see, we're running up against time here, so I think we'll do one more question. But thank you guys for keeping these questions coming. So for our final question, we'll ground it in New York State here. In the question askers area, rural area north of Albany, they have brownouts several times a year. Should they expect battery energy storage systems to help eliminate or mitigate some of those brownouts?
So I
I'm
think
going to start that one. So is that a yes?
Go ahead, Jason.
I'm going to sound like I'm punting on the answer, and I really don't mean to. It's a difficult thing to say yes definitively. If you think about the typical storm that would come through, say an ice storm, and trees topple over and transmission or distribution lines go down, the restoration time is largely what's driving that. So the two things that storage would assist with is it would allow you to be able to isolate sections of the grid better so that you're not taking everyone down. There's also switchgear that can help with that. The other thing that it would do is allow at least a portion to have electricity either wholly or, dedicated facilities if it's a critical facility. And so if the question were something like we typically have a 36-hour or 48-hour outage, would storage solve that? The answer is not on the grid side. The best solution in that case would probably be something directly at a homeowner, which may frankly even include some type of a fossil fuel generator that's just downsized to be able to provide long-term resiliency. Or you would go in and determine which circuits have to be run in the house, heating, for instance, some basic lighting, some refrigeration, in order to get a longer duration out of the storage.
All right. Well, with that, unfortunately, there are, a number of additional questions, but we are running short on time. So I just want to say again, my sincere thank you to Dr. Stan Whittingham and to Jason Doling for joining us here. I'm sorry, if you wouldn't mind pulling the slides back up one more time. We've got one more just sort of plug for, again, 2 weeks from today, we will be joined by a representative of the Office of Fire Prevention and Control. Next slide, please. The OFPC, as well as the Energy Safety Response Group. That will be event number 2 happening on May 19th, again at 5:30 p.m. We hope to see all of you there. If you have any questions in the meantime, please do feel free to reach out. You can reach our team at cleanenergyhelp@nyserda.ny.gov. You can also find on our website a link to the Battery Energy Storage System Guidebook for local governments, and soon you'll be able to access the slides and recording of this presentation there as well. So again, my sincere thank you to all of you for making time. I hope you're about to go off and eat some dinner. Thank you for joining us, and we'll look forward to seeing you in a couple of weeks.